Hi, my name is Raphael Memmesheimer and today I present our work entitled Skeleton-DML, a deep metric learning approach for skeleton-based one-shot action recognition. We are with the Active Vision Group of the University of Koblenz-Landau in Germany. So let's start with an example application of what our approach is capable of. A robot observes a human that performs an action. The robot recognizes that it has not seen this activity before and initiates a dialogue to associate a robot behavior to the observation. The observed action serves as a reference sample to associate a robot behavior. A single reference sample is enough to handle the observed action the next time. Note, in contrast to classification or action recognition approaches, this requires generalization to unseen data and unseen classes especially. And this is where Skeleton-DML comes in. So Skeleton-DML is based on transforming skeleton sequences to image representations and learn a metric that encodes action similarity. So first, we represent the skeleton sequence as an image, and in contrast to many other representations that use the RGB channels to disentangle X, Y, Z values of the joints, we locally group all X coordinates in the first block, all Z values in the third block, and all Y values in the second block. Details are given in the paper. And during training, the encoder optimizes the distances in embedding space for self-positive negative pair similarities. We achieved this by using a multisimilarity minor and a multisimilarity loss. The resulting encoder allows then to estimate action similarity by calculating distances in the embedding space. And note that during the training time, no actions from the test set are used. So they are completely distinct, and especially important is that no classes have been seen during the training time. So when talking about the training set, in case of the one-shot action recognition protocol, they are also referred to as auxiliary training classes or an auxiliary set. So here we give an overall overview of our approach. So first we encode all skeleton sequences of the auxiliary set into our image representation, and then we jointly optimize our model using ResNet for transformation in the feature space, and from this feature space we use a metric loss for the transformation into an embedding space. In our experiments we exchanged different minors and different losses for optimizing the embedding space. Then, having the encoder model or embedding model, we can use the skeleton sequences to transform all reference samples into our image representation, and of course all test classes, and then we can use our encoded model to associate all test samples to the reference samples by finding the nearest neighbor in embedding space. At test time, given a single reference sample, similar actions can be associated by a nearest neighbor search in embedding space. This is how this can be visualized. And note, high distances encode different actions, and low distances encode action similarity. And if there is a high distance to all reference samples, this is considered to be an anomaly or novel action class. And we executed a huge set. We executed an extensive experiment setup with different representations like the TSSI representation, gimme signals, scalar motion, SLDML, skip pixels, and Skeleton-DML representation that we proposed in this paper. And we found that our approach outperforms the SLDML baseline by quite a huge margin, starting from having 80 training classes and 100 training classes. With a lower amount of training classes, we are outperformed by the SLDML baseline. Also, we outperformed the dataset baselines by the authors of the NTU RGB+D 120 dataset, starting from 40 classes. And in our experiments, we also examined the influence of different metric losses, embedding sizes, augmentations, and training set sizes. The code for Skeleton-DML is publicly available on GitHub, and we want to thank you for your attention.